Hello students, welcome to part C of chapter 2, Chemistry Comes Alive. We just finished up talking about chemical bonds, the different types of chemical bonds. Now we're going to discuss section 2.5, it's the very last part of the basic chemistry in this chapter, which really focuses on how these bonds get made, how they get broken, how do we make stuff. So chemical reactions, really. And a chemical reaction occurs anytime we make a new bond, we arrange some chemical bonds between atoms, or we break bonds between atoms. And so every chemical reaction, every chemical equation has both the reactant, what's going through the changes, and the products, the stuff that comes out at the end. And so here you can see we've got some hydrogen gas and some oxygen gas. They come together and we get 2 molecules of water. So the reactants are over here, the products are over here. And they must be balanced on either side of the equation. There are 3 kind of patterns in terms of chemical reactions. We have synthesis reactions, which make stuff. We have decomposition reactions, which kind of breaks apart stuff. And we have exchange reactions, which both breaks apart stuff and makes new stuff. Let's look at a synthesis. Literally, A plus B becomes A plus B. So we have some small molecules coming together to form larger molecules. And so this is the formation of bonds. This is what we call an anabolic process. It's going to require energy. Decomposition reactions are the exact opposite. Now we have molecule AB decomposing into its constituent parts, A plus B. It's literally the exact reverse of a synthesis reaction. And so this is the breaking of the bonds. And this is a catabolic process, which releases energy. In the example here, we have glycogen, this big, large kind of storage molecule, and it gets broken down into these little tiny glucose molecules. And the breaking of the bond between the little parts of the glycogen releases energy, and we call that a catabolic process. Exchange reactions are where bonds are both broken and then kind of remade. So sometimes we will call them a displacement reactions. So here we have molecule AB, we join it with C, and we kind of exchange the B for the C, and we end up with AC plus B. So here, for our example, you can see this ATP molecule transfers its one kind of terminal phosphate over to this glucose molecule, and we end up with a diphosphate molecule here because we have 2 phosphates, and glucose phosphate as one of our products. You may have heard of redox reactions before, what we call oxidation reduction reactions. These are a specific type of decomposition reactions that occur as part of our digestive process. So all of our food energy, this is how we get it, is through this redox process. So not only are they decomposition reactions, because stuff is falling apart, breaking down, but they're also exchange reactions because electrons are exchanged between the reactants. So not only are bonds broken so that the large food fuels can get broken down, the electrons themselves are actually hopping between these different reactants. Let's look at an example. So here is the redox reaction for glucose. You can see here's our little glucose molecule. Glucose loses all its electrons, it loses its hydrogens, and it basically becomes carbon dioxide. So it's oxidized because it's losing electrons. And then oxygen, you can see here, becomes water, and since it's gaining all those electrons and hydrogens that the glucose gave up, it is considered reduced because it's getting more of that negative subatomic particle in the form of the electron. We really have kind of two ways that energy kind of flows, kind of whether we're talking about anabolic or catabolic. In an exergonic reaction, we get a release of energy. So all of our oxidative reactions, like that redox reaction we just looked at, and all of our catabolic reactions, whenever we're breaking a bond, we get a net release of energy. And that's because the products themselves have less potential energy than the reactants, and so some of that energy is free and available to do work. Conversely, endergonic reactions have an absorption of energy, and that is because their products have more potential energy than the reactants. And so these are anabolic reactions. These are synthesis reactions that are going to require energy input to make something new. And that kind of makes sense, right? If you're going to make something new, that requires an energy input. Let's look at a chart. I think it's kind of easy to see in a chart. So here you go. You got an exergonic reaction. The products have less energy than the reactants, and so we get kind of a net energy release. Here with our endergonic reaction, the products have more potential energy than the reactants, and so we have to input energy to make these particular products, to make this reaction occur. So these are catabolic reactions that release energy, breaking things down. These are anabolic reactions, synthesis reactions, inputting energy to make new things. Theoretically, every chemical reaction is reversible. Right? Theoretically, A plus B becoming AB could go the other way around, where AB becomes A plus B. Most reactions will occur in, theoretically, both of these directions, both the forward and the reverse reaction, until an equilibrium is reached, where neither of them is dominant and they're kind of both occurring simultaneously. However, this is just in theory, because in our bodies, essentially, for all intents and purposes, all of our biochemical reactions are irreversible, in part because there's a lot of energy that's required. The molecules that are involved move through the body. They can get removed right away. They can become something else. And so even though theoretically all of the biochemical reactions that take place in our body are reversible, in practice, not so much. In terms of the rate of reactions, this is one of the reasons that we require a normal body temperature, because if our body temperature increases or decreases, that will affect the rate of chemical reactions, the rate of the reactions that take place in our body. So you can see an increase in temperature would increase the rate of reactions. Conversely, a decrease in temperature would decrease the rate of reactions. Chemical reactions are also sped up if we increase the concentration of the reactants. If there are more of atom A available to do something with, then of course we're going to be able to do more of it. If the particle size decreases, that also increases the reaction rate. That is because smaller molecules, smaller particles, have, essentially think of it like a closed system, right? If you have a very small container and you put lots of little things in it, the chance of them interacting with other little things is pretty high, as opposed to just having like maybe a couple large things in there. And then the really big important one here, aside from concentration, particle size, and temperature, is catalysts. So catalysts are any kind of compound that increases the rate of a chemical reaction without actually becoming different. So the catalyst remains the same. It doesn't change. It doesn't become part of the product. It just affects the rate of reaction. And so what we're really talking about are enzymes when we're talking about the human body. All right, that's it for part C of Chapter 2, and that is the end of the Part 1 Basic Chemistry, General Chemistry. The rest of these lectures are going to focus on the second half of Chapter 2, which is the biochemistry.